Folks, hello and welcome to your final discussion post here in week 5 of Math 222. We have saved the most important concept of the course for week 5, and that's this idea of relations and functions. And perhaps outside of the idea of equality, this idea of relations and functions is probably the most fundamental to the basic idea of mathematics. You will see here that what I have done is instead of showing you the list of problems that are assigned this week, what I want to just talk about very quickly to introduce this is the notation and some of the definitions that you are going to come across this week, and the basic idea of graphing functions and how they are manipulated or transformed by taking a basic function such as y equals x squared, or f of x equals x squared, or f of x equals the absolute value of x, or f of x equals the square root of x, just as simple examples. And what we're doing to a graph, or the visualization of a graph, how it's transformed by the manipulation of the function itself. So very quickly here, as you've gone through the reading, you know that if we're looking at this idea of a relation, in its simplest form, a relation is a set of ordered pairs. And if you want to think of it as a first coordinate and second coordinate, or x coordinate and y coordinate, it's very simply an ordered pair. And typically, when we have an ordered pair, such as an x and y coordinate, somehow they are related, hence the idea of a relation. And the idea of a relation is fundamental in the fact that when we say that we go beyond that to the idea of a function. Folks, hello and welcome to your final discussion post here in week 5 of Math 222. We have certainly saved the best for last, and that's this idea of relations and functions. With the exception of equality, I would say up to this point, everything you studied in Math 221 and 222, the most important idea is this idea of relations and functions. As as we begin to build on your mathematical background, we certainly want to become more and more aware of the applications where we can use math to model certain situations and understand certain situations. And the idea of relations and functions is certainly the most fundamental way to do that, and the most important concept that you should understand as you sort of look forward here to more and more applications of really kind of the basic algebra that we've looked at in Math 221 and 222. As you see from this week, I'm not showing you the discussion post page. What I have done is I've actually pulled up the example because I want to talk about these definitions, some notation, and this idea of transformation of graphs and how it happens. So I know if you're at this point where you're getting ready to start your discussion post, you've already been through the reading and the homework, and you have come across these words, but I just want to go back and reinforce these very quickly. And then we'll move on to, again, some of the notation and some of the ideas here that we talk about in terms of transforming basic graphs or basic functions. But first off, let's start with the idea of a relation, and let's just say very simply that a relation is a set of it's a set of ordered pairs. And typically, when we talk about a set of ordered pairs, we know that there's typically a relationship between the first component in that ordered pair and the second component in that ordered pair, and we can very simply call them typically we would call them the x component and the y component. That's very practical or familiar naming convention. When we go from this idea of a relation to this idea of a function, we know that going from relation to function, there's a greater demand being put on a set of ordered pairs when it is called a function. And what we probably have seen and has been sort of the emphasis when you start talking about the difference between a relation and a function is that in a relation, in an ordered pair, the x coordinate can be repeated and have many associated y components. For example, the ordered pair 2, 3 and the ordered pair 2, 4 can be part of a relation. However, when you go to a function, there is this added restraint, or I should say constraint, on a function that if you look at the set of ordered pairs, and if the x coordinate in a set of ordered pairs would happen to repeat itself, then it must have the same y component. For example, if I had the ordered pair 2, 3 and 2, 3 in the same function, that's okay because 2 is being associated with 3 in both cases. But if I had 2, 3 and 2, 4 and I was trying to consider that set of ordered pairs a function, I would not be able to do that because 2 is repeated as that first element in the ordered pair, but it has a different value as the y component. So it's very key to understand the difference between a relation and a function. All sets of ordered pairs are considered relations, but in order to go from a relation to a function, you have that added constraint that you must have for each element, each first element or each x coordinate, the associated y component must be unique. And so a very key difference this week between relation and function. We've talked a little bit about domains of functions. And again, what is the domain of a function? Well, it's the set of all real numbers that can be substituted for a variable in a function. If you're naming that function with some sort of equation or mathematical relationship, it's the set of all real numbers that can be substituted for the variable. And when you sort of, I think the easiest way is you put the number in the machine and you turn the crank, and what comes out on the other end, it better be a real number. And typically, we get very, very concerned about the domains of functions when we talk about rational functions, and we saw that in the very first discussion post. Actually, in week 1, when we talked about rational expressions and finding the domains. Obviously, when we start dividing by 0, so any real number that makes the denominator of a rational function 0, we get concerned about that because division by 0 is undefined. And then the other one we get concerned about here, and here's the example right in front of you, is that when we start taking the square root of a number, we know that in order to produce a real number, that radicand, or whatever it is that's underneath the radical sign, that value must be greater than or equal to 0. So anytime I have a negative number under the radicand when I'm taking the square root, that is not going to produce a real number. So you have to be very careful about the domains of functions when you're dealing with something that's rational or it involves a square root. We'll leave it at that at this point, or a radical situation. And again, so we talk about domains, and then the idea, what is the range of a function? Well, it's the set of all numbers that once I turn the crank on the relationship, it's what comes out on the other end. And typically that has a range of values. You'll see this particular function that is being discussed here. The range looks like it's only real numbers greater than or equal to 0. And that's typically, we would think of that again as something that we are taking the square root of, and there you see the function right there. You're never going to take the square root of a number and get anything less than 0. So it makes good sense here that what comes out of the square root function here is just real numbers greater than or equal to 0. Let's see. As I go through the rest of this discussion post, or this example for you, again, just be very cognizant of the difference between a relation and a function, domain and range. And then the final idea this week is how functions are transformed by either adding something to the function or adding something within a function. And let me sort of explain that here. For example, here, what you see is the basic function here is the absolute value function. And if I looked at just the function, the absolute value of x, I'm sure you've seen something in a textbook or one of your homework problems that looks like the visual of it is a V with the pointy end sitting on the origin, the entire graph sitting above the x-axis, other than the point that touches the origin. So what we're going to start doing here is, how is this function transformed when we have the negative of the absolute value, and what does this what does this 1 here that's really being added to the function, how does that change the picture of the graph? And when you have something that's, and I say sort of external to the function, this element here, or this added constant here, is going to give you what we would consider to be vertical translation. So it's going to move the basic graph up and down depending on the value. As compared to, and I apologize for rotating back there, but let me just go back. If you look at this function here, where if the basic function here is obviously the square root of x, and you know that sort of looks like a small curve that starts at the origin and kind of moves to the upper right. The difference between this function and the one that we saw below is that, remember, we had a 1 that was added, what I would say sort of outside the basic function. But here, if you look at this as f of x equals the square root of x minus 1, where the minus 1 here is actually under the radicand. When we start manipulating the function within itself, and I say within the square root function itself here, this gives you horizontal translation. So this would actually move this function. It would move the point that was touching the origin. It would actually move this 1 spot to the right. And so you have to be just cognizant of, again, and I hope I explained this okay, where in this case the function was being manipulated itself by the fact that we were subtracting 1 under the function, right? This idea of this being the kind of the base function, the square root of x, as opposed to this idea here where the base function here is the absolute value of x, but the added constant here is sort of outside. It's not the absolute value of x plus 1. It's being added outside the function. So again, and that gives us a vertical translation. So I hope this helps. And again, what I want to really stress this week is being sure that everybody's clear how to distinguish between a relation and a function, and the domain and the range of a function, and this idea of vertical and horizontal translations of functions and how they happen. One last thing, while I see it right here, there's a discussion in your book about something called the vertical line test. And if you're looking at the graph of a relation, the way that we would further confirm that that relation is in fact a function as well is by applying the vertical line test. And that is, take any vertical line and place it on top of your graph, and if the vertical line only touches the graph 1 time, then the relation is in fact a function. But that is in your reading and something that you can take a look at as well. So again, our last and final discussion post here for week 5. And again, this is kind of the bread and butter of Math 222, this idea of relations and functions. And as you go forward in any other math course, you'll certainly see the application and the value of relations and functions. And so it's very key terminology that we get nailed down this week. So if there are any questions as you go through the discussion post, let me know. This one is very involved and a lot to it. But again, let me say one more time, this is kind of the bread and butter of Math 222, and we want to certainly send you off and onto your next courses with a strong understanding of the verbiage, the definitions, and the notation. So have a great week, and let me know if I can do anything to help you on this discussion post.